The most common data type used across most languages for storing lots of data is the array. So C, Java, arrays are very common. Even Python, it's called a list, and it has some of the functions we're going to talk about built in, but it's still fundamentally an array under the covers, if you will. So understanding the advantages and limitations of arrays will help us understand why these other more advanced data structures are out there, and also understanding when an array is possibly more appropriate versus when a list is more appropriate. So the thing to remember about arrays is arrays have fixed memory. This hopefully isn't a new concept for you, but may not be something you talked a bunch about in your introductory programming class. But when we go and define a pointer to a thing like a string, this is Java syntax, but it's very similar in C and other languages here. But when we see this, we create a pointer, and the pointer is a space in memory. So again, the idea is to create some storage space, and the storage space then gets created based off of some size. And so the size that's going to be stored is going to be based off of what I'm storing. So think of it this way. If you go to the pet store and you get 10 mice, you could have a cage that it's probably a good size cage, but something you can carry around by hand. Where if you get 10 dogs, you probably need to, have some sort of kennel created and have somebody come in and put some fencing. Where if you get 10 tigers, you probably need a very, very, very big cage that's going inside of there. And if you get 10 elephants, you can see it scales up. So what gets stored helps determine the size of what gets stored. But it's a fixed set of memory. It's all set aside at once. Again, if I'm going to go make my elephant preserve, I buy one big chunk of land that's all connected, and the elephants can run around inside that land. And each of them can have their space. So I assign that typically by jumping straight to whatever location in memory I want to. And in this case, I'm putting the letter C out there at the third location if you're dealing with a base 0 language. And now you can kind of understand a little bit why languages start at 0, because the formula behind this is you, oops, I hit the wrong button. You are taking the memory address of the array, so whatever location this is. So let's say it's at memory address 10, and there's 10 items here, and each one of them is a size of 2, let's say. So it's normally, it's a string here, which is a little bit confusing in that a string can be way more than 2 bytes of information, but pointing to the string would be 2 bytes of information, which is the way a lot of languages do this, is they point to the actual data stored somewhere else in the memory space. But again, if it's 2, then that means the first element is at address 10, the second element is address 12, the third element is address 14, 16, 18, and so on. And so I can figure out where to put this C in memory, the letter C in memory, the string C in memory also here, by saying the index, which is 2, times the size elements of stored, which is 2, so 4. So it's 10 plus 4, and that's the location it shows up as. So the great part about this is it's really quick and easy. If I want to find something in memory, I do a single multiplication, a single addition, and I found it. I'm done. That's those 2 quick little steps, and I can find anything I want to. It's kind of, if you think about it, if you want to find somebody's house, most of the time you just got to drive up and down the house and look for the number. But if you know that all the lots on a block are exactly 50 feet, then you don't have to guess. You can just say, okay, well, I'm going to walk 350 feet because it's the 7th house down, and it's going to be somewhere right there. And that's basically the way an array works. But the important thing to remember about arrays is the initial value in the arrays are always dependent on the language. Languages like Java will initialize an array to appropriately 0 values, either a 0 for integers or a null character, or a address of 0, 0 if it's pointing to something else. Where languages like C, they don't waste the time doing initialization. They assume that's your responsibility. And so an array could be filled with data because that's whatever was there on the memory ahead of time. Think of it this way. You either buy a house that's been painted for you, or you buy a house with whatever junk's on the wall because you probably are going to paint it anyway. And Java is the one that makes it all nice and clean before you walk in, and C is like, hey, you do the work. You tell me. I'm going to save you some time and money by not doing anything that you don't want me to do ahead of time. So arrays are super efficient locally. Um, this is not this is an analogy. It's not the best analogy, but kind of think of them like the taxi cab of moving people around. If I want to go from point A to point B in town, taxis are really efficient. If I want to go from New York to Chicago, taxis are less efficient. Um, Again, the analogy starts breaking down here a little bit because the idea of efficiency means something a little bit different. But as the scope gets bigger, it becomes less able to manage that. That route gets bigger. There's a famous story, a famous scenario around taxi cab drivers in London. You see, in London, to get a taxi cab license, you have to take a test of how well you know the city. And London's a massive city, and there's tens of thousands of places to memorize and streets to remember. And taking that test takes years and years and years to be able to get good enough to do that. And it literally changes the brain map of how London taxi drivers, process and remember that information. Um, but that is a lot of effort. It's a lot of time to manage. So really, you can think about it, it's this simple case as well. Do you want to have to, if you fly into a new city, go off and find a taxi cab company and find their phone number and call them, or know somebody and flag it down? That's essentially what arrays are. It puts all the onus on you, the coder, the taxi cab customer, the one who wants to ride, to go figure all that out. Where mostly what happens is you see something like this picture, you go to an airport, you have a taxi stand. You go, you stand in line, and the next person up jumps in, and they go, and it's a list that's going on inside of there. Essentially, it's a queue, more accurately, as far as data structures go. But you have a ordering to things, and so we can actually take the notion of an array and all the craziness around it and convert it into a list, an ordered structure. And so the first key we need to do is not just have the array be, well, there's this size and I don't know how many elements are in it. We need to track the number of items in the list. We're using the array as storage. So we have a count here. You can call that whatever you want to. I actually call it something different in different implementations. A common term for this is index, because it's which item has been filled. I think I called it last index in my implementation of the assignment you'll be working on here in a little bit. But count is good enough for now. It's how many items are in this array. Now notice I initialized this array to be size 10. It'll hold items 0 through 9 as far as indices go, but there's 10 items in the array. And then the add simply adds the value at the count. So the first thing that goes in goes at space 0, and then I increment it by 1. The second thing goes in at space 1, I increment it by 1, and so on. So turning an array into a list is not too bad to start with. We just use the count to know where the next item on the list goes to, and the size of the list is the count, that last array index. So to manage that list size then becomes pretty simple up until the point we hit the 11th item going in the list, at which point we get, again, the Java message here, an array index out of bounds exception. It's the similar things will happen in C, Python, whatever language you're using, but the concepts are here, and I'm just using Java code as a simple syntax that's kind of a good bridge between many languages. So the idea behind this is that I have a problem in the sizing, but it's a problem that I can fix fairly simply. All I need to do is say, okay, well, if the count is equal to the size of the array that I set up, well, I just need to make my array bigger. And I can do that with this simple little algorithm where I take a copy of the existing array, but then I point it to a new bigger array, in which case I'm making an arbitrary size 10 bigger. Different algorithms do it differently. They either increment by a fixed size, or they make it 50% bigger than what it was last time. There's pre-built solutions for you, but just understand you can always choose to build your own strategy depending on how it goes. If you have something that's very, very fast growing, exponentially growing, building it by half again or doubling the size every time makes sense. If you have something that doesn't grow very fast, maybe just adding a fixed amount, a few here, a few there, is the appropriate solution. Generally speaking, if you have a fast-growing data structure, arrays might not be the best way to store it, but we'll see that later on as we talk about linked lists. But again, once I have created a new data structure, I have to copy the old values into the new values in the same order in which they were. So the great part about a array implementations is that they allow me to quickly reference data items. They allow me to quickly add them, change them, up until the point I've run out of space. So think of it, like the example we saw before on a piece of paper. I can write stuff down a list on a piece of paper until I've run out of space. And that at that point, I have to get a bigger piece of paper. But in order to do that, I've got to copy it over to a new piece of paper, everything that was already there. Yes, I could just tape on a new piece of paper, but that's a different data structure at that point. That's a linked list when we talk about it. So remember, the rule behind the array list is they all have to stay in one cohesive structure, one nice bit of memory that I immediately know exactly where I can increment and make it bigger. All right, so theoretically, it's all downhill from now. So we know we have a data structure. We have an array, and we have this counter, this index, this size manager that tells me how big the array is, where the last item goes to next. So the arrays, we already showed how to add an item. You got to be able to retrieve items. Easy. I just index the array, whatever item you want to. Update items, easy. I just set the indexed item that you told me to the new value. Remove an item, a little bit harder. I go to the index you want me to, I pull that one out, and I move everybody up one space. I mean, think of it this way. If you have a row of people sitting in an audience and one of the people get kicked out, everybody else who wants a better seat stands up, moves one seat to the left, and sits down. That's essentially removing an item. Tracking the size is easy. I have an integer to do that. I tell you what the last index is. That's the size of the items. And querying the contents, well, I can just loop through the values. And we'll see this. We're going to practice this, actually. That's the next assignment that we're going to talk about. And we'll talk about that again in a separate video. But the key here is, now that we have a data structure, the whole process is about finding the correct algorithms. So once you've set the data structure and the value proposition of that data structure, then everything else is downhill. Arrays, again, work really well as a data structure when I don't have data growing fast. And when it is, then we can choose lists, as we'll see in a little bit. But the next thing you're going to do is look at building a list out of an array data structure.